All right. So last class we talked about regression. So far we've talked about machine learning, and we said machine learning is a way to enable computers or machine to learn from data, to learn from experience without explicitly being programmed. And we said there are majorly three types of machine learning. We have the supervised learning, the unsupervised, and the reinforcement learning. But we said for this course, we are focusing on supervised learning. And what makes it supervised is that for a given data problem that we have, in the data, there is something called the target or the label that can give guidance to the features in the data, that can give guidance to the model in order to predict the target or the output variable. For instance, to give an example, so I want everybody to be muted. If you're not muted, I will remove you from the class. Okay, so we gave an example of a regression problem where you want to predict, even one is there, you want to predict the sales of what a product given the YouTube views of that product. Like you did an ad for a product on YouTube, and you want to predict the sales of that product given the number of views that you have. So the views, the YouTube views will be the variable, the feature, and your output, the target that you want to predict is the sales. So because you have the sales as an example in the data, that makes it a supervised learning. And then we said the supervised can be further divided into two, which one example is what I've given. One is regression and the other one is classification. The classification is when your goal is to predict a category given a number of features. Like you want to predict whether an image is cat or dog. You want to predict whether a transaction is a fraud or not. So this can lead to, this is what we call fraud detection. Or you want to predict whether a customer of a particular product or company will churn or not. Churn means will leave the company for his competitor, or not. So things those are classification problems. Okay, so that's we've been focusing on. So last class we talked about linear regression, which is a type of regression. And linear regression can also be simple linear regression or multiple linear regression. Simple is when you have a single variable, a single feature. And multiple linear regression is when you have more than a single feature, like you have two variables, two features that you can use to predict that you have in the data, right? So most of the time in the real world, and the example we gave, like the lab session we had, you used that was a multiple linear regression because you have more than a single feature. And in the real world, you will not be using a single variable to predict the target, right? So most of the time, the features can be many. It can even be as many as 100, 200. So the problem now becomes which of those features are needed in building the machine learning model. So that is where feature selection will come in, and that is where data understanding will come in. You will need to understand the data, do a lot of visualization to understand the impact of each variable in the data. You will need to talk to other people who are more familiar with the data to explain, to understand each of the variables or the variable you should be focusing on or things like that. And that is where you will spend most of the time. Apart from cleaning the data, if the data is cleaned, you also need to understand which feature, because not all the variables in the data will be relevant to the goal. Okay, so you will need to understand. Otherwise, if you just build the model with all of the features, those irrelevant features will also affect the performance of the model. Okay, so because the model will need to understand the relationship between each of the variable to the output that you are trying to predict. So if many of the variables are not really contributing, they are going to make the model perform poorly. So where most people spend their time on, apart from cleaning the data, when you get to building model, it is feature selection. There is a way to do feature selection, but I'm not covering that in this course. Okay, so, but if you're interested in doing, there's a way you can, there are a lot of materials on feature selection, how to select features that are needed. There is a mode, like there is a class or a function that can actually weight each of those variables and give, for instance, if I want to look at another model called random forest, there is a part in that random forest called feature importance that can help us rank the importance of each variables in the data and give us an idea of which variable we should be focusing on. So I can use that to select the features that are important and then build my model on those features alone. So you can do that, but that's nice when you have many features. But for the sake of this, we're assuming all of the features in the data are relevant. But in the ideal world, it's not going to be like that. Any question? Is it clear what I'm trying to pass across? Is it clear?
Yes, sir.
All right. So we did linear regression, and we were using a very small data, and we realized that the model overfits to the data. So we said one other way to reduce or combat overfitting is what we call regularization. And by regularization, it will mean we want to restrict the model. We want to restrict it to a specific values of those coefficients or the weights, because what I've told you that for machine learning, the model is actually learning how to come up with the right values of those W's, those weights in the data, or those coefficients of your linear regression equation or model that will help predict the actual targets. So regularization is a way to restrict those coefficients, because the essence is this, that when high values of those coefficients will lead to, is what majorly made the model to be complex. So high values, each variable, the values of each variable determines its impact on the model. So variables with high coefficient values means that the model is really contributing, is making more impact on the model. So if all the variables have high values, the model can become complex for the data at hand, except you have large amount of data. So most times, what we do is to regularize that model. That means restrict the values of those coefficients to be small, make them small as possible. Okay, so unfortunately for linear regression does not have any parameter that can be used for regularization. It doesn't have any argument or parameter that can be used for regularization. So that's why researchers come up with two types of regression that serves as a regularization model to the linear regression. The first is the ridge regression. And the idea of the ridge, so it's also a regression, okay? But the goal of the ridge regression is to regularize a linear regression model. Okay, so how does it do that? So it only achieves that by the particular distance it uses. I won't go into the detail of the distance because it's more mathematical, but the distance is called L2 norm. It's just your normal Euclidean distance. For those of you who have understanding of mathematics a little bit, it uses Euclidean distance. So it measures a straight line between between the variable and the target. Okay, and then determine, so the one with high distance will have high impact on the model. The one with small distance will have small impact on the model. So what it does is that it tries to shrink or reduce that coefficient to be small as possible, to be close to zero, but not exactly zero. So that's what I put here, that it shrinks high impact coefficient or high impact variables to nearly zero. So when it looks at the model, after you fit the model, it looks at the variables that have high coefficient, and it tries as much as possible to reduce those coefficients to be small as possible, to be nearly zero. Okay, that's, however, it doesn't reduce all variables. It only reduces the variables that are not so important in the model. It reduces them. It reduces their value to be small, to be close to zero. What the idea of that is that if a variable has a coefficient close to zero, it simply means that that variable is not contributing very well to the model. So that means that the variable have lesser impact in the model. So it's not contributing so much. So that way, that will reduce the complexity of the model. So if you do not do feature selection and you use Ridge or all this regularization example Ridge, for those variables that are not contributing so well to the model, it's going to reduce their coefficient to be close to zero. So most people find this better and useful instead of spending most of their time on looking for the features that we contribute well. They use all these Ridge and the second one we're going to discuss as a form of feature selection, because it reduces the impact, it reduces the coefficient of those variables that are not contributing very well to the model. It reduces their coefficient to be close to zero. So thereby, but features that contribute very well are not tampered with. How it does that, it uses the distance formula, which I told you, the L2 norm, which is like Euclidean distance. Okay, so we will see how we can implement this in Python using scikit-learn package that we started using last week. So we'll see how we can implement that, but that's the theory behind it. It shrink the coefficient or the weight of variables that are not so important to be close to zero. Is it clear? Is Ridge regression clear? Hello?
Yes, sir.
Yes, sir.
All right. Okay, so let's look at the second one before we look at how to implement this. So the second is Lasso regression. So Lasso uses, there's something we call L1 norm, L1 distance. So that is, instead of, I don't want to go into the mathematics, but it's just like an absolute value of those coefficients. I will show you the formula when we get to scikit-learn, the lab where you see it, I will show you so that you can see the formula. It's there. So it uses like an absolute value of those weights of, so it takes it, but Lasso is a little bit harsh. So the idea we Ridge, remember, Ridge will reduce the coefficient of less important variables to be near to zero. However, Lasso will turn them to exactly zero. What's the implication of that if the coefficient of a variable is zero? Who can tell me? What do you think? What's the implication? What does that mean?
It won't affect the model at all.
Exactly. That variable is completely out of the model. So that's what it's doing. So a lot of people, so there is a debate. Some people prefer Ridge because it shrink them to nearly zero, meaning those variables still contribute. However, the contribution is minimal. But some school of thought goes with Lasso. I'm part of the school. I'm in between. Now, I personally am in between both. I use both sometimes. But if your goal is to do feature selection mainly, then Lasso regression is the way to go, because Lasso is just like select the variables that are important. Every other variable that are not important, I don't want to use them. So that's what Lasso is doing. It turns them exactly to zero. But if all the variables are important, it's not going to do anything. It's not going to turn them to zero, just going to leave them. But if you find variables that are not contributing to the target value, it's going to turn them to exactly 0. So meaning those variables will not be used in building the model. Is the difference between Lasso and Ridge regression clear?
Yes.
All right. So if this is the case, this one will be next week, logistic regression, because that's where we're going to, that's the other part. This is where your project will be focused on. Like, I mean, if I have time, I can introduce one more classification, but the goal is just a logistic. But if I have time, I can introduce one more, maybe k-nearest neighbor or random forest, whichever one. So, but this your project will be on classification, or I can mix it up anyway, depends. But you will see I will upload all the project during the week. Okay, so let's see. Okay, so let's see, so I've explained all of these. So we're just going to kick off with the same data we used last week, and I'm going to just use the function we already defined. That's the essence of function, is to reuse them so that I don't start from the scratch again. So I'm just going to bring out this function that we use, that we define for processing the data. So I'm just going, since we are using the same data, I'm just going to call this function. So that function is data processing, and it takes the URL and whatever the label is in the data. So if you remember, it selects the features and the targets, and then it splits the data into twofold, the training and the testing, 75% to train, 25% to test, and then it scales the data. Who can remind me why we scale the data? Anybody? Why do we scale it? Nobody, because people did not watch the video. Yes. So if people don't, you don't practice during the week, you don't do anything, or what? Shane, why do we scale the data?
We use either min-max scaler or standard scaler.
I said, why do we scale the data? Are you there?
Yes, sir. Yes, sir.
Is it that you are thinking about it or what? I said, why do we scale it? Or you don't know?
Can't remember, sir.
Okay. All right. So since you people did not read, I'll leave that one for you to to figure it out. So we scale the data. We scale the data, and then so this is scaling the data. We fit transform the training data. So the fitting is to calculate, since we're using the min-max scaler, the fit there is calculating the minimum and the maximum. And then we use the minimum and the maximum to transform the training data and the test data. And then finally, we return the scaled data for the training and the testing. Okay, so I just need the name of the function. All right. Okay, so the goal here is to import the Ridge regression, and then we'll bring in the data. We've already processed it. I don't need to go through that again. And then we pass that the processed data to the Ridge regression, and we build a model out of it. And then we can see maybe later, maybe if the performance is not so well, we can visualize the Ridge. We can try to regularize the model using different values of the regularization parameter and then visualize it. Okay, so from scikit-learn linear model, we import a model called Ridge. Okay, so let's define a function for our ridge regression. Maybe we'll call it ridge reg. This person is coming. Okay. Okay, so let's bring in the data. So we have the X train. Let me be sure what does it return here? Okay, return the training, the testing, the Y train, and the Y test. Okay. All right, so we have X train, X test, we have Y train, we have Y test. Oops, sorry. So the model is called data processing, and it takes the URL. Okay, maybe we should even pass this model should take in a parameter called URL, since this one is taking URL and label. So we can even pass a label to read so that it uses whatever label this one has. Okay, so this one is optional anyway. It is optional to whatever you use as argument. So I want the model to carry a URL and label and then pass it to this. Since we know this function we already defined takes in the URL and whatever the label is in the model, in the data. So once we pass it, that is going to process and return the processed data for the training and the testing. So the next thing is to instantiate our model, the ridge regression, just like we did linear regression. So we will call the ridge that we've just imported, we instantiate it there, and then we're done. We fit it. We just do fit, and we fit it on the training set. And then we can check the performance on the test set, on both the training and test set. So let me just copy what we've done here like this. Let me just copy this too. So this will give us the accuracy on the training and the testing. If you don't understand what I'm doing, please feel free to ask. So ridge. Any question? Is this clear? Is it clear?
Yes, sir.
Okay. So all I need to do is to call back my function. I'm passing the URL we've already defined. So this is the URL. Let me bring in the URL. That's the URL for the data. So I'm just going to bring in this URL. And I know the label is MEDV. That's the median housing price. Okay, so let's put the URL here and then call the URL. Then the label is MEDV. So if I do this, oh, sorry, it's supposed to be regression reg, that's the name of the function. So if we do this, look at the training accuracy and the test. So it's not so different from linear regression, but we've only, this ridge regression, how does it do the regularization? Let's look at the parameters there. So the parameter that actually does the regularization is this alpha value. Alpha value. So the idea is, so if you read the documentation, this is the L2 norm I was telling you about. You can see linear least square with L2 regularization. So this is the alpha constant that does the regularization. So the higher the value of this alpha, the more the regularization you are applying on your model. The smaller it is, the smaller the regularization you are applying on your model. So by default, it uses an alpha value of 1. So sometimes you may want to adjust these values. You may try to run this model multiple times using different values of alpha and visualize the result, the training and the test for each value of alpha, just to see which values of alpha is actually the best to run the model. So when you do that, after running it for, like, let's say you try 5 or 7 different values of alpha, whichever one gives you the best model is that value you will now use to rebuild your model, your ridge regression model, you using that particular value of alpha. So that's the idea of visualization. So we can do that here too. We can import matplotlib and then visualize it. But it seems that this model, this data is very small. So the model may not really perform very well, even with regularization. But we're actually just doing this just for you to see how you would do it for large model. Okay, so import matplotlib.pyplot as PLT. So we can try to specify a particular values of alpha that we want to run a for loop on. So we can do alpha. Let me just copy this and redo it. So what I want to do is to set different values of alpha, maybe alpha values, and list different values. This one is arbitrary. You don't have to use exactly this. So I want to try 1.2. I want to try 5. I want to try 8. I want to try 10, and maybe 20. So I want to try these 5 values. So for these 5 values, I will run a for loop that for alpha in my alpha values, you did for loop. So if you have not forgotten, for alpha in my alpha values, we want to run this model. Okay, for alpha in my alpha values. So what I'm going to do is that each time I'm running the model, I will set the alpha. I will set the alpha here, the alpha there, to be whatever alpha this is picking. Do you understand what I'm trying to do? Any question here? Please feel free to ask questions. Any question on what I'm doing here? Is it clear to everybody what I'm trying to do here?
Yeah.
Can you summarize what I'm trying to do, Awele?
We want to run a for loop to pick for the alpha values so that we can change the alpha values in the ridge regression.
That's right. So each time, so this model is going to run 5 times. The first time is going to pick alpha value of 1.2 and build a model. Second time, 5, like that. So we can also have a training. Let's open an empty list for a training accuracy where we can store the training accuracy, and also empty list for test accuracy where we can store it. So what we do is that for each alpha value, we'll fit it on the training set, and then we'll append the accuracy, this accuracy like this, we append it to that training accuracy. So we'll do train accuracy dot append, and then we append the training score and also the test score. So for each time we run the model, instead of manually doing the 5 times, changing the values, we can just run it 5 times and then append the training and test accuracy. So at the end of this for loop, there will be 5 accuracies for the training and 5 accuracies for the testing. Each one corresponds to each values of alpha. And then in the end, we can visualize. So I don't need this again. So in the end, we can visualize the training accuracy and the testing for each values of alpha. Since I've imported matplotlib.pyplot, so I can do plt.plots. See, import matplotlib. Yeah. So, and then I will pass in the, so I want to plot the alpha value that will be on the horizontal against the first time is a train accuracy. And let's use the label of training accuracy. So I will also plot the alpha values against the testing accuracy. And that's all. So alpha values against the tests accuracy, and then we change the label too. So, and then we can give you legends so that you can show the label. You can say location should be best as you deem it fit. And then finally we show it. That's all. So once we run this regression model again, instead of showing us the single accuracy and this is going to show us a plot of the training and testing for each values of this alpha, if everything works well. Okay, so let's call the Ridge, is it called Ridge model, Ridge reg? And then we'll pass in the URL and this MEDV. So if we run this, you can see, so this gives us a plot now of the performance of the training of the model on the training and the testing set for each values of alpha. So what do you think is happening in this model? Anybody? Is this model, what do you think is going on? Anybody who want to try? Awele, what do you think?
I think the model is still overfitting.
That's
for
right.
all the values of alpha.
That's right. So you know this now. So at this point, you can conclude that the data is maybe too small for the model. So you might, since regularization doesn't work, and you've shown it. That's why visualization is good. That, so you've tried different values. You've tried increasing the regularization parameter, the alpha values. From 1, you use 1.2, you use 5, 8, 10, and 20. And for all the values, the model still overfit. Why do you say it overfit? The training accuracy was far higher than the test accuracy across all the regularization parameter. In fact, if you want to be sure, we can decide to decrease the regularization. Maybe instead of 1, let's use 0.2. Let's add those one. Let's add 0.3 and 0.5. So if you run this and run this again, see, it's still the same. So it's not because we increase the value. We try to use values less than the default and values above it, but the model still overfit across all values that of the regularization part. So this might mean that the model, the data is too small for the model, and that's true. The data you use was about, I mean, we can check the shape. We can check the shape of this guy when we call the data pre-processing. You can check the shape. The shape was actually small. The test was about maybe 137 thereabout. So, and the training was also small. The training was about maybe 300. So the data is actually a very small data. So at this point, your best bet could be to get more data. So we can apply the same concept for Lasso regression too. I've explained Lasso that it tries to shrink the coefficient to be exactly 0 and not use them. So I'm just going to copy this same model. The only thing I'm going to change is just the only thing I'm going to change is the name. I mean, we can do the same thing for but I'm sure Lasso may not work if we change the alpha value without changing something else. But for just to explain it, let's do that. So let's see, let's change this to Lasso model. So, but before this, we also need to import the Lasso regression. So from the scikit-learn linear model is also a linear model. Import Lasso. Okay, so what we're going to change, we'll change this to Lasso, but I will tell you that we're going to get error because Lasso requires that if you are changing something, there's something we need to change in that parameter, but we'll see that. Let's see. So sometimes it's good to drive home the point by making mistakes so that you can see what doesn't work. Okay, so I think everything is fine here. So let's run this and then let's call the function here. What?
Read.fit.
Is it what? Oh, okay. See, sorry. Thank you for that catch. Okay, I think everything is fine now. So let's see. Lasso model, passing the URL, passing the MEDV. So we're going to get, okay, it still works. So look at Lasso. Oh, okay, that one is in Logistic Regression. There's something, okay, this is fine. So look at Lasso regression. What do you think is going on here? Or which one do you think is better?
So I think Lasso is actually shrinked or something like that from the diagram you're seeing here, from the visualization.
Is doing what?
Very shrinked, like it's shrinked together.
And you know, the concept of Lasso is to shrink the coefficient of the variables in the training set that does not contribute to the performance of the model. So his goal is to reduce the effect of overfitting. And I think he's doing that. If we look at these plots compared to this, Lasso appears to be better. You can see that at some point, at the beginning of one, the training was still like the model overfit. The training was around 70% and the test was around 55. But as the values, as the regularization increases, the training begins to fall. The same thing with the test. However, it got to it, but the training wasn't increasing across the values beyond that. So at some point, everything became zero. So that means you want to try an alpha value of something like, I mean, the default value is still the best, the default value of 1, because at 1, then both model is around, I mean, the both model is now like both data set, the trainer and the test, the performance on both are not too high again at 1 or 1.2 thereabout. But as you increase the regularization, Lasso will be restricting, will be reducing the impact on the model. So it got to a point that everything became 0. So you don't want any value from 5. You don't even want any value from 2.5. So maybe something from like 1 or 0.5 will be fine. Okay, so you can see that's the impact of Lasso. It's going to shrink them to 0 at some point. Yeah, so but that's because it still feels that some variable, hello, muted, who is that? So that's because it feels that some variables in the model, in the data, are still not contributing very well to the performance. Sean, please be muted. Why are you unmuting? So that is it. So it's feeling that, I think it still feels that some features are not performing, they are not contributing well to the model. That's why the shrinking continue. But for some data set where all the variables in the data are very important, the lasso may not shrink them. So I will leave that one for you as an exercise here, but I want you to try both on this data called USA housing. You have it in the regression data in your dashboard. You have it here, this regression data is there. You have the USA housing there. If you have not downloaded, download it. So try it, make sure you build the linear regression, the ridge and the lasso, show the plot just like I've shown you for the model, for the 3 models, or the 2 models, I mean, that's on ridge and lasso, and see if there is going to be any difference. So you can do that now, or if you want to do that assignment, fine. But if you want to do that now, you can quickly do that. But there's already an assignment in for you. So this is a separate data. So this is your assignment for the week, and the assignment is due on Thursday. After Thursday, you will not be able to submit it. And if you are submitting your GitHub link. So this is the assignment. So the assignment, the data and the description of the data is there. So it's not on housing or anything. So the description, the output variable is there. So, but this assignment is due Thursday night, Nigerian time by 11:59. So, yeah. So after Thursday, I won't grade it. So, because all you need is basically what we've done here. So it shouldn't take you much time. But use the idea of a function to define a function for processing the data up to scaling, splitting, and then define a model, another function for your model. Okay, so that's it. You can even try to generalize your function for your model. Instead of building linear lasso separately, ridge separately, I can define a function called model that takes in the model name, the URL of the data, and the label. I can do that so that I won't have to. So all I just need to do is call the model, passing the general model, passing the whatever model I'm talking about, maybe lasso. I will just pass in. This is what I will pass in, the lasso and just lasso in bracket, empty bracket, just pass it in. That's the model. And then the URL of the data. And then you are going to do all of this. So it's going to take the name of the model and do whatever you are doing there instead of manually calling lasso here. I can do that, but I will leave that one for you to see if you are truly learning and you understand all these functions, all these loop that we've done before. Define two functions. One function to process your data, which would be to get the data, split them, normalize them. I'm not sure the data has any missing value, so it doesn't need cleaning, but split them and normalize it. Another function is a general model. It's called model. The function should take in the function should take in the name of the model you want to build. So you can do that for, maybe for Lasso regression or Ridge, taking the model name and then the URL for the data, if you like, and then the label, the output variable. So build the linear regression. So you only need to call the model 3 times. The function 3 times, which is the model 3 times. The first time passing the linear regression name model, second time passing the lasso, third time passing the ridge, and it should give you your accuracy. Then you can now fine-tune that function to focus mainly on ridge and lasso, but showing the visualization across the regularization parameters, just like what you have here. Am I communicating? Is what I'm saying making sense?
Yes, sir.
Yeah, so
yes, sir.
So that means you are defining 3 functions. One to process, one is a general model, which we just show the accuracy for linear regression, ridge, and lasso. The third one, it should be like this. It should also be another general model, but the model should be for lasso and ridge. But so and the idea is because linear regression, it doesn't have regularization parameter. So that's why you are defining another one. So that one should also take in the model name, maybe the URL and the label. But this time around, you are going to run in across different values of alpha. You choose yourself. It doesn't have to be this value. Choose alpha values yourself. But the more the alpha values, the higher they are, the more the regularization. Just know that. So, and then run a for loop through. You can choose like 10 values. Run a for loop through those alpha values and fit the model, whatever model you are calling, instantiate them, fit them, and append the score, just like this idea, and then in the end, plot them. So when you are calling the model, you are only calling the model 2 times now. The first time will be for Ridge, the second time will be for Lasso. But each time you call it, it should display the visualization of the performance on the training and test across the alpha values. Is it very clear? Hello, is it clear or is it tough? Is it hard? You guys are not talking. Is it clear? This one you answered by laughing. So is there anybody called Sheye Banjo here? Anybody? Nobody. Okay.
So it's me. I'm Sheye Banjo.
Oh, okay. So you are your midday. Okay.
Yes, I'm Adi Banjo.
Oh, okay. All right. So that's it. So that's the assignment. So everything I explained here is not explained in the README file. It's not explained in the description. That's what I'm explaining here. All you have in the description is the description of the variables in the data. So I'm not promising, but if I have time today, maybe I will adjust the README file and put all this information. But the essence of it is the assignment is for those of you who are in the class. So I've explained it now. If you like, jot down, make sure you do it. Try as much as possible, and you can seek for help. However, in the US, there's something called plagiarism. That's the same standard that we use. If I see your code, I will know if you plagiarize. So
can't you make it over Stack Overflow?
See, there is a way. Seeking for help. Let me stop recording now. So